Alright, we're going to do this again with the second reaction. This is a fusion one. Notice we're taking some small nuclei, combining them to make large. So this is similar to what's going on the sun right now. Hydrogen is being combined together to form helium, and again another neutron. That neutron is there to create another hydrogen, which will combine with another hydrogen and again fuse to create helium. I give you some numbers in the notes that talks about the amount of energy being produced on the sun per second. This is the ideal type of nuclear reaction. The products are not harmful, like you can see in the videos, and huge amounts of energy per nucleon are being released. In fact, I'll compare this final answer with the final answer we got in example 1 and prove to you that the amount of energy released through fusion is greater than the amount of energy released through fission. So again, we do this the same way using Einstein's formula. E equals change in mass times speed of light squared. Let's start again with the mass of reactants. So that's going to be the 2 hydrogen, 3.3444 times 10 to the negative 27 kilograms plus 5.0082 times 10 to the negative 27 kilograms. So the mass of the reactants, I punch them in. Exponent negative 27 plus 5.0082 exponent negative 27, 8.3526, 8.3526 times 10 to the negative 27 kilograms. Find the mass of the products. It's going to be equal to the mass of the helium nucleus, 6.6463 times 10 to the negative 27 kilograms, plus a neutron, 1.6749 times 10 to the negative 27 kilograms. It's 0.6463 exponent negative 27 plus 1.6749 exponent negative 27 gives you 8.3212 times 10 to the negative 27 kilograms. Again, probably did this right because my reactant mass is slightly bigger than my products. So the change in mass is going to be 8.3526 times 10 to the negative 27, subtract 8.3212 times 10 to the negative 27. My change in mass (3.526) exponent negative 27 should give me 3.14 times 10 to the negative 29 kilograms. So there's my change in mass again, similar to how we did in example 1. A little bit easier because we got less particles or less numbers to add. Now I'll go to the next slide and calculate my energy released. So go into Einstein's formula. E equals change in mass times speed of light squared. 3.14 times 10 to the negative 29 kilograms times 3.0 times 10 to the 8 squared. Energy equals 2.826 times 10 to the negative 12 joules. And since we converted the last one to electron volts, let's do that as well. So divide by 1.60 times 10 to the negative 19, and we should get electron volts of 1.77 times 10 to the 10 to the 7 electron volts, or 17.7 mega electron volts. Now you may be a little bit puzzled because this number is not as big as the example from number 1, and I'll explain that in a quick second. First of all, you just have to make sure you find the mass defect, multiply by the speed of light squared, and then you can leave your answer in joules or you convert to electron volts, no big deal. Now, to explain why this number is smaller, what we need to go is we need to find the energy per nucleon. So I'll do this on another slide here. In example 1, we calculated with fission a typical fission reaction. We had energy equal to 191 mega electron volts. Example 2, we did a fusion reaction and we calculated an energy of 17.7 mega electron volts. The trick is, in example 1, the total number of particles, total nucleons, was 236. We had 235 of them with uranium and 1 neutron. So when you take this number and you go energy per nucleon, then you get a slightly different value. It's going to be 191 mega electron volts divided by 236 gives you 0.809 mega electron volt per nucleon. When we compare to example number 2, the number of nucleons in here before and after was 5. Totally different story here. The total nucleons in this case is 5. So if you were to find the energy per nucleon, this one's going to be, yeah, it's a smaller value, but a lot less nucleons. 17.7 divided by 5 gives you 3.54 mega electron volts per nucleon. And that's why I told you that fusion can be many times greater than fission. Even though the number that I calculated was smaller, this is dealing with a lot smaller nucleons. So you're getting a better bang for your buck, I guess, kind of thing with fusion than with fission. And that will kind of help you explain or understand that little graph I have at the end of the lesson that shows you the very steep part of it being at the fusion end, and it actually being a lot smoother slope on the right hand side, which tends to be with the great big elements that break by fission. You may get a larger number with fission, but the energy per nucleon is not as big as the energy per nucleon with fusion. And that's why cold fusion is the hot new thing in nuclear physics that probably will be developed sometime throughout this century. They'll probably be at that point where we can do cold fusion.